Following the rapid post-war electrification of railways, alternating current AC electrification, with its lower construction costs, increasingly extended to rural areas. While electric locomotives initially mass-produced AC-specific units that converted AC to direct current (DC) to drive DC motors, EMUs took a different path. For DC-driven EMUs, unlike locomotives, which consist of many units, the increased quantity of complex and expensive AC equipment was a disadvantage in terms of vehicle costs. Even though the advent of silicon rectifiers overcame the complexities and maintenance weaknesses, the device costs remained disadvantageous. Various attempts were made to use the induction motor, which was seen as the dream motor, but all failed. After many trials and tribulations, EMUs also adopted DC motor drive through rectification. For passenger and freight trains operating across both DC and AC sections, locomotive replacement could handle the transition, although it was cumbersome. However, this approach was not viable for EMUs. To enable through operation, control devices compatible with both power sources were necessary on the vehicle side. During the period when only resistor control was available for DC sections, AC equipment merely converted the overhead AC to 1500 VDC to supply the DC control equipment. This meant that the high-efficiency power conversion by transformers and the high-adhesion performance from voltage control, rather than current control, which were the greatest advantages of AC electric trains, were completely wasted. Additionally, the DC EMUs, which were lightweight, became significantly heavier due to the addition of these devices. Initially, the advantage of high power supply to mainline trains offset these drawbacks. But this benefit was not realized in short-formation trains on local lines. Amidst this dilemma, electrification began in Hokkaido. Similar to the situation previously discussed in Shikoku, both were not connected to the main island, Honshu, by rail at the time, so there was no need to consider through trains for DC sections. Naturally, there was a strong push to introduce specialized AC electrified vehicles. Due to the larger transportation units compared to Shikoku, the simplified AC electrification method considered for Shikoku was not applicable. Instead, a method common with Honshu's AC electrification was adopted, and AC-specific EMUs were developed. Although the method of rectifying and driving DC motors remained unchanged, the AC system's voltage control through transformer tap switching eliminated the need to consider series parallel connections of the motors, allowing all to be connected in parallel and thus achieving high adhesion performance. Around this time, with the adoption of magnetic amplifiers in the ED75 and the practical application of semiconductor thyristors, phase control became more accessible. By continuously varying the conduction time, it became possible to continuously change the motor terminal voltage, eliminating one of the weaknesses of resistance control, the shock during resistor switching. This significantly reduced the factors causing wheel slip. Moreover, voltage control had the advantage that, when slipping occurred, the motor torque would quickly decrease, leading to a natural stabilization of the slip itself. Despite issues with performance degradation due to ripple and the impact of harmonics on surrounding circuits, these advantages were considered to outweigh the problems. Thus, the 711 series EMU was born. Given that these prototype EMUs were the first to be deployed in a full-scale cold region, changes were made not only to control and running gear but also to the structure of the car body and underfloor equipment, producing two different two-car sets for comparison. One set featured unit windows, as adopted in the Tokai type and later models, using paired glass for improved insulation. The lower window was fixed while the upper window was designed to slide down, enhancing airtightness compared to previous models. The entry doors were the folding type used since the new series diesel cars, strengthened against freezing and drafts. The other set used sliding doors, with windows of the same double-glazed construction as the Kiha 22, featuring FRP window frames to reduce heat conduction. In terms of performance, the high adhesion performance was leveraged, considering the possibility of hauling 2 trailer cars with 1 motor car on flat lines like those in Hokkaido. Although classified as suburban EMUs, they were designed with enough performance for express operations, necessitating a certain level of high-speed performance. However, to achieve this performance with a 1M2T configuration, the conventional reduction gear ratio for express EMUs of 4.21 was inadequate for acceleration, while the 4.82 ratio used for suburban EMUs resulted in insufficient high-speed acceleration. Developing a new high-power electric motor would require additional development costs and time, diminishing the benefits of AC electrification on unprofitable local lines. Thus, the bold approach was to drive the existing MT54 motors at high voltage to maintain torque at high speeds. These motors had a history of being used in electric braking mode, where the generated voltage exceeded the rated voltage, without insulation issues. This is where the advantage of AC systems, which can freely adjust voltage through transformers, came into play. In conventional DC EMUs, even in the final stage of parallel control with 3 notches, the motors are connected in a series of 4. Therefore, the overhead line voltage of 1,500 volts, divided by 4, limits the supply to no more than 375 volts. The MT54 was designed with a rated voltage of 375 volts. However, as mentioned earlier, it had been used above this voltage during electric braking without any issues. By supplying 500 volts, it was possible to maintain the rated tractive effort at higher speeds. When a DC motor starts to rotate, it begins to function as a generator, as the basic structure of a generator and a motor are essentially the same. The electricity generated opposes the voltage supplied for driving, working to prevent current flow. This causes a drop in rotational force, so the controller reduces resistance to maintain current flow. However, once all resistance is removed and the supplied voltage reaches the motor directly, no further control is possible. To address this, the generator function must be weakened to allow more current to flow at the same voltage. A simple method involves bypassing the field winding with a resistor to weaken the magnetic field. This is known as weak field control. While this reduces the generator's function, allowing easier current flow, it also weakens the motor's magnetic field, thus reducing its tractive effort. Without the bypass, as the rotational speed increases, the drop in tractive effort is more significant. Therefore, in DC vehicles at the time, where voltage could not be freely controlled, this weak field control was used to minimize performance degradation at high speeds. In contrast, the 711 series could supply up to 500 volts, making weak field control unnecessary and ensuring tractive effort did not drop at high speeds, achieving a similar effect as having a lower gear ratio. As a result, it achieved nearly the same performance as express EMUs with the same gear ratio as suburban EMUs. By maintaining high tractive effort up to high speeds, the motor output was significantly increased from 120 kilowatts to 150 kilowatts without any special modifications to the motors. However, despite the absence of the weak field mechanism, bypass resistors were connected in parallel to the field winding to address ripples from single-phase AC rectification, effectively keeping the motors in a constant 5% weak field state. While the motor output was enhanced by over 20% without changing the weight, the AC vehicles carrying heavy transformers inevitably had a weight disadvantage. To fit all equipment into one motor car, they omitted the braking resistors by sacrificing the regenerative braking system to reduce weight, yet the loaded weight still significantly exceeded 50 tons. For DC motors, which feature exposed commutators and brushes that emit electrical sparks, managing cooling air in snowy, cold regions is crucial. The lower the temperature, the finer the snow becomes. If cooling air draws in snow, it can reach the motors and melt, causing insulation failures and rendering the train inoperable. To prevent this, a machinery compartment was installed at the end of the car, where air was drawn in by an electric blower and directed through a dedicated passage under the passenger compartment floor. This passage was heated by the cooling exhaust air from the motors, melting any snow mixed with the outside air. This setup ensured that snow did not reach the motors, eliminating snow-related problems. To accommodate this passage, the floor height was raised by 75 mm compared to conventional cars. For the underfloor equipment's snow protection, two methods were employed: packaging each device and enclosing all equipment except the transformers, akin to a body mount system. Consequently, parts other than the transformers were painted the same red as the car body, giving a distinctive appearance. The passenger compartment heating was heavily reinforced for cold climates, with not only enhanced heaters but also ventilators capable of heating intake air, trialed in trailer cars. Additionally, for the first time outside of limited express services, heater power control was automated. Thus, two types of test formations were completed. The first dedicated AC electric train for conventional lines, fully equipped with cold and snow-resistant features, was ready to face the snowy challenges of Hokkaido.